Hello viewers, today I discuss this idea of Banach space in functional analysis. It's a very important part. Let's watch till the end. I discuss today this introductory level. At the first stage, we consider a Banach space at first. We study it today, and now we have to require, there's a prerequisite elements, that's a linear space. If we consider it as an L, suppose it's a linear space, and this linear space is not only L, the combinations of the order triplet L, and another is dot, and another is a field. Dot or multiplicative, whatever may be the multiplication, dot or cross, whatever may be, we take as it's possible, where this L, that's called additive abelian group, and as usual know what dot is, and F is called field. You already know from abstract algebra. And we consider another function, we choose it as like this u, and that function takes the form, that's an external composition, F cross L, that's map onto L, this additive abelian group. In this way we consider, and whose value if we note it as external composition, that is alpha x, that's the notation where alpha be the element of the field and x is element of any abelian group, and that's a dot product, that is order triplet alpha x, and where any element, if we called, that's the additive abelian group, and dot is the external compositions, dot or cross, whatever may be, but as usual notation, this dot we use it, and this is a Cartesian product L to L, this map, and this is denoted by alpha x, and such that this alpha beta element, if we choose whatever may be extension, that's called F, and if we take xy be the element of additive abelian group L, and then we have where we find that's taken, where we have the following properties. Properties we follow, that's property number one. Let's watch till the end. For number one is, if we take alpha be the elements of any field and external composition operated with x and y, that's the element of L, we find it as alpha x plus alpha y. And in the next stage, if we see that alpha plus beta be the element with x, that element goes to alpha x plus beta y. This is the property. And property number 3, if we choose it as alpha beta x, that's a property of associativity, alpha beta into x. And elementary number 4, that is a property of some unit in ring 1x, that is x, and this is where this 1 is here, the multiplicative identity. Multiplicative identity of F, that's a field structure if we consider, and the number of L, the numbers of L are called vectors, and those number, that is those of f, are called scalars. And here the operations u, there's a function, if we take as a function, so the operation, if we take as by notation u, is called scalar multiplication. So L is a linear space over S. So L is a linear space over F, that is a field. So in this way we study our idea, the introductory idea of Banach spaces, especially in linear spaces. And these chapters we use the field F, and F is the arbitrary field, and where F can be any real number or complex number, either real or complex, and the linear space is called a real linear space. And if we take as a real number, and if we take complex number as a field F, then it will be called a complex linear space. A linear space have both real or complex. Next we start non-linear space. Let's watch. Now let n be a complex or real, whatever may be, linear space. We use the notation n here because we are studying non-linear space. That's why we study it and we are writing in this manner, because our study is restricted for n-less or non-linear space. That's why. And let this norm function, if we consider it, so be a function from n to r, such that for all, if we consider x, y, if it categorically belonging to n, and for all alpha, if we consider it belonging to C or R, whatever may be, real number space, then we have number one postulate: if norm of x is non-negative, is greater than equals to 0, non-negative. Second postulate, this norm of x is equal to 0, that's imply and only imply x is 0. And third postulate, that's a property x plus y, this is the property that will be less than equals to norm of x plus norm of y. And number fourth property, that is norm of alpha x, that will be mod alpha and norm of x. These are the norm functions, and it is the extensions of mod, that is norm, that's in dimensional cases. So the function this norm notation in this way is called a norm on n, we defined, and the pair, as we technically write it in this manner, n and norm, it's a notation, is called a complex or real non-linear space. or shortly NLS in this way. It is our notation NLS. And the real number, that is norm of x, that is called a norm of the vector x. It is norm of x.